Hello, welcome to the Silicon Labs Dev Lab. I'm Martin Looker. During this Dev Lab, I'll walk you through the creation of an AI ML Bluetooth magic wand that will have the following features. An RGB LED will be used to indicate the status of the device. It will connect to a Bluetooth light. Pressing buttons or drawing gestures in the air will turn the light on and off. The use of a pre-built AI ML model will detect the gestures when fed with data from an accelerometer. Before you begin this workshop, you'll need some hardware and software. For hardware, you'll need two Silicon Labs boards. The first can be any board that supports the Bluetooth protocol, which we'll be using as a light. I will be using a BGM 220p Explorer kit for this purpose, which is one of our entry-level Bluetooth boards. For the second board, which will act as the magic wand, you will need an XG24 dev kit board, which features a multi-protocol AFR32 MG24 wireless microcontroller and includes many sensors on the board. We'll be making use of the accelerometer for this project. As we will be drawing gestures in the air with this second board, you will either need a long enough USB lead or a coin cell to power the board. You can find links to both these boards in the video description. For software, you'll need the Simplicity Studio IDE installed. Simplicity Studio is free to use and can be downloaded for various platforms from the Silicon Labs website. The EFR Connect mobile application, available for Android and iPhone from the relevant app stores, can be used to check the operation of the light device. Finally, a terminal application like TerraTerm, will be useful for observing debug messages output by the application. You'll find links to all these software applications in the video description. Before getting started working with applications, I want to spend a few minutes talking about the benefits of running AI ML on an edge device. There are several factors driving this kind of processing to the edge. Privacy, security, cost, latency, and bandwidth all have a part to play when evaluating where to perform AI ML processing. Some applications, like autonomous driving and navigation, require extremely low latency. Other applications, like speech recognition, can generate privacy concerns when personal data is transferred through the internet for processing. By moving AI ML processing to the edge, latency, cost, and bandwidth can all be reduced, while increasing confidence in privacy as collected data never has to leave the edge device. Tiny machine learning, or tiny ML, allows the AI ML processing to be performed in low energy systems like sensors and microcontrollers to perform automated tasks. When using tiny ML, you can do more with less. The techniques are still machine learning, but with lower energy and costs and without the need for an internet connection. The majority of ML at the tiny edge is based upon detecting events locally on the device. Sensors such as acceleration, temperature, current voltage, and also time series data from ADC or GPIO inputs can be used to detect anomalies and perform pattern matching. Microphones can be used to match patterns, such as glass breaking, or to detect wake words, with a low-power device waking the parts of the system that consume higher power to perform its tasks, or even to react to command words directly. Cameras, including fingerprint readers, that provide low-resolution images can be used to read fingerprints, compare snapshot images for always-on vision, and to classify and detect images, objects, and gestures. In all these cases, the low-powered edge device can act upon the event, and connected devices can communicate to control other devices as a response to the event. The typical use cases for tiny ML include health monitoring and elderly care applications, tracking biometric signals to predict or identify health disruptions, and detecting falls. In these cases, deviations from normal signal variations are detected and acted upon. For the smart home, voice and gesture control of devices can be achieved by using audio or vision pattern matching and keyword detection. Predictive maintenance to predict or identify breakdown, which reduces unplanned downtime and allows timely maintenance prior to failure. In the security arena, noise detection, such as glass breaking, can be detected. Smart locks can be operated, and people detected and counted to avoid false alarms. Before we begin working with AI/ML and the magic wand, we need to create a Bluetooth server device to control. For this, we will use the Bluetooth System-on-Chip Blinky demo application from Simplicity Studio that can be used with the EFR Connect mobile app to control an LED and monitor a button on the BGM 220p Explorer kit. This Explorer kit is a low-cost entry-level board. The BGM 220p module on the board includes an EFR32 BG22 Bluetooth system-on-chip. The board has a single button and LED that can be controlled from software, but it is also very expandable thanks to the micro bus and quick connectors. Plus, you can add headers for general access to the pins. You don't have to use this particular board for the Bluetooth Blinky demo application, as it's available for all our boards that support the Bluetooth protocol. Later on, we will control the Blinky device from the Bluetooth AI/ML magic wand that we will create in this dev lab. The Bluetooth Blinky application is provided as a pre-built demo in Simplicity Studio. It is also available as a project with code, allowing it to be used as a starting point for building your own applications. We'll see that process in detail once we start creating the magic wand application. To flash the pre-built demo into your board, you'll first need to enter the launcher perspective in Simplicity Studio. Then make sure your board is connected over USB and select it in the Debug Adapters panel. The launcher will then display information relevant to the connected board. To get to the example project, select the Example Projects and Demos tab. As you can see, we have many demos and examples for this board. If you're looking for something in particular, you can filter and search using the controls on the left. I'm going to enter Blinky in the search box as I know the name of the project I'm looking for. We have two options here. The box with the Create button will create an example project in Simplicity Studio with code that you can examine, build, and alter. This box marked Demo with the Run button will simply program the pre-built binary into the selected device. As this is a Bluetooth application, it requires an appropriate bootloader to be programmed alongside the application. For the Bluetooth demos, this is done automatically, but I'll show you how to select, create, and program the correct bootloader when we move on to the Magic Wand application. Let's start up EFR Connect on my mobile phone and work with the Blinky application. This default screen is the scan screen, which is available from the scan button in the center of the lower toolbar. From this screen, you can connect to any Bluetooth device in range and explore the functions it offers over the Bluetooth connection. However, we have a specific GUI in EFR Connect to interact with the Blinky application. Pressing the Demo button in the lower left of the toolbar will open the Demos screen, and from here we can open up the Blinky GUI on the center right. Once we start this demo, it will ask us to select a nearby device named Blinky Example, and when we find it, we can connect to it by tapping it. The light can be controlled by tapping on the screen. In the default application for the Explorer kit board, only the onboard LED 0 will be operated. But you can see here I'm making it a bit more obvious what's going on with the use of the LED matrix I have attached. The button is also monitored. When the button on the board is pressed and released, the GUI will be updated accordingly. Loading demo applications is a really easy way to explore the capabilities of boards. If a demo has features you are interested in, you can create the example project and explore the code to see how it works. We'll create an example project in the next part of the hands-on. We now have a Bluetooth server device operating as a light that we can connect the AI/ML Magic Wand device to control it over Bluetooth. Let's take a quick look at the board I'll be using for the AI/ML Magic Wand device, the XG24 dev kit. The Dev Kit boards are a step up from the Explorer Kit boards, like the one I just used for the Blinky application, in that they have an extra button and an RGB LED. But the main upgrade is a large number of sensors that are ready fitted, making it an excellent board to use to prototype a wide range of wireless applications. We'll be making use of the onboard accelerometer to collect movement data, which will be fed into the pre-built AI/ML model for gesture recognition. There is also a quick connector, making it easy to add even more sensors and peripherals if the device you require is not already in place. The microcontroller on this board is the EFR32MG24. This is a multi-protocol wireless device. In addition to Bluetooth, which we'll be using in this video, it also supports IEEE 802.15.4 based networks like Zigbee, Thread and Matter. Another useful feature of this board for our Magic Wand application is the slot for a coin cell on the rear, allowing us to power the board while picking it up and drawing gestures in the air. There is also a connector for an external battery if you want longer battery life. For AI/ML applications, this microcontroller really stands out in that it features a matrix vector processor that can act as an AI/ML hardware accelerator. The benefit this provides is that it offloads processing from the main CPU, leaving it free for application processing. The MVP in the MG24 provides up to 8 times faster inferencing over Cortex-M and up to 6 times lower power consumption during inferencing when running standardized benchmarks from the independent benchmarking body mlcommons.org. For Bluetooth-only applications, the recently released BG24 platform also features an MVP. I mentioned bootloaders when we programmed the Blinky demo, and an appropriate one was automatically included when we flashed the board with the pre-built binary. We'll also need a bootloader to load the Bluetooth Magic Wand application we're going to create. We could just program a demo into the board to get the appropriate bootloader into Flash, and then replace the application binary with the Wand application we're going to use. But I think it will be more useful to show you how to create, build and flash the appropriate bootloader from within Simplicity Studio. I'm back in Simplicity Studio's launcher, and this time I have the Dev Kit board that we were just looking at connected rather than the Explorer Kit board. And once again, I'm in the Example, Projects and Demos tab. Searching for empty will reveal this Bluetooth SoC empty example project, which contains a framework for creating Bluetooth applications, which we're going to use as the starting point for our Bluetooth Magic Wand application. If I open up the project documentation for this example app and scroll down, near the bottom we can find a list of compatible bootloaders. We'll be making a SoC project to run on the MG24, which is a Series 2 device. Therefore, we need the Bluetooth App Loader OTA DFU type bootloader. Let's close the documentation and find that bootloader project. This time, let's search for App Loader. And here we can see the bootloader for the SoC Bluetooth App Loader OTA DFU that the README referred me to a moment ago. And I can click the Create button to begin the process of creating the project. In the new project wizard, I prefer to add the board number to the project name, as I may create this same project for different boards and chips in the future. I can then click the Finish button to start creating the project in Simplicity Studio. When the project is created, Simplicity Studio will automatically switch to the Simplicity IDE perspective and open some useful files related to the project. We'll look at these in more detail when we start creating the Magic Wand application. For now, I just want to build and flash the bootloader into my board. Building is accomplished by selecting the top level project folder in the Project Explorer on the left and clicking the Build button in the toolbar, which has a hammer icon. Output from the build is displayed in the console panel at the bottom. And if there are any problems with the build process, like warnings or errors, they'll appear in the Problems tab. With the bootloader built, you will find a binaries folder under the top level project folder. And inside here, you'll find the binaries in various formats, We're going to make use of the .s37 file by right-clicking it and selecting Flash to Device. In the Flash programmer, I'm first going to ensure that my whole flash is erased by using the Erase button. Then I can program the bootloader binary into Flash with the Program button. We now have a bootloader binary programmed into the dev kit ready to boot our Bluetooth Magic Wand application. The process we just followed to create, build and flash this example is exactly the same for all the other example projects you'll find in the launcher. Just check which bootloader, if any, you'll need for the project you're creating. Let's take a short break from Simplicity Studio to summarize machine learning. There are in general two main approaches when it comes to machine learning. Classical machine learning, where training data is used to adjust generic algorithms to provide the desired output. Algorithms such as linear regression, support vector machines, and others. And neural networks. In this case, we have layers of operator nodes simulating the brain's neurons. The nodes receive the output of the nodes from the previous layer. Each node has a weight value assigned to it, and training data is used to adjust these weights so the whole network provides the expected response. So for example, if we feed the network with a cat, we expect to get the label cat as an output. Of course, the same would be expected even if the input data is slightly different, but still a cat. And along the same line, we expect that if completely different data is introduced, the network can effectively classify it as not cat in this case. Both methods have the same end goal, which is performing inference, meaning that new data is fed into a trained model to get a result. Two common use cases are supervised learning, where labeled data is used for training so the network can classify new inputs into one of the classes or labels the model was trained with. And unsupervised learning, where unlabeled data considered as normal is used to train the model so the network can generate internal patterns and detect anomalies in input data that differs from the normal data set used for training. So how can a neural network be implemented on embedded devices? In a very simplified way. The first step is to train a model. This is usually done on a PC or server, as the process is resource intensive, and for this, a data set called training data is required. Typically, this data is made of features extracted from the original raw data through pre-processing. The output of the training process is a trained model, which is a file describing the neural network operation. This can be deployed in an embedded application to perform inference on input data. This model can be seen as the connection point between the data science or machine learning domain and the embedded software application domain. It's important to note that any processing done on the data for the training process should also be done on the embedded application's input data for the model to work appropriately. Overall, this is the concept behind edge computing, where computation and storage are moved closer to data sources, in this case the embedded device itself. Now we'll turn our attention to creating the Magic Wand application. We'll be using the Bluetooth empty example project from Simplicity Studio as our starting point. The empty example acts as a Bluetooth server, advertising its presence for other devices, like mobile phones, to connect to, and then allowing the exchange of data. The Blinky demo that we are running as a light acts in this way as a Bluetooth server device. Our Magic Wand, therefore, needs to act as a Bluetooth client device, scanning for the Blinky device and connecting to it in order to control it. We'll be altering the server code we get from the empty example to work as a client, in addition to adding support for the LEDs, buttons, accelerometer, and the all-important AI/ML functionality. I'm back in the launcher perspective in Simplicity Studio, and I have my dev kit connected and selected. And once again, I'm in the Example Projects and Demos tab. So I'm going to search for empty once again. And here we can find the Bluetooth SoC empty example project. Clicking the Create button will begin the creation process. In the project creation wizard, I'm going to remove empty from the project name. This isn't going to be empty by the time we've finished working on it. And I'm going to name it 1D in keeping with our Blinky application. And just like I did with the Bootloader project, I'm also going to append the board number on here in case I were to make this project for a different board in the future. Then I can click the Finish button to create the project in Simplicity Studio. Just like with the Bootloader, we'll return to the Simplicity IDE perspective with some files opened automatically. The first is the README for the empty Bluetooth example. There's some general guidance on accessing further information on working with Bluetooth, including the bootloader information we saw a short while ago. Other examples will have information relevant to the example being created. Another file that is opened automatically is the Bluetooth GATT configuration file. This file contains the database that specifies the Bluetooth profiles, services, and characteristics offered by the device. The Magic Wand application will not make use of these, and we could delete many of them. I'm going to leave them in place to speed up our Magic Wand development, as they will not cause any issues. The Magic Wand application will instead discover and manipulate the services and characteristics contained in the Blinky device's GATT database. If you are creating a Bluetooth device, you can use this GUI to configure the functionality it offers. If you want to discover the contents of the Blinky device's GATT database, you can explore it through the EFR Connect mobile application, or create the Blinky example project in Simplicity Studio and take a look at the GATT configuration file you'll find there. The .slcp file contains project configuration tools. From the Overview tab, you can find information about the board and the SDK the project will use when building the application, together with some quick links to the most used tools and files in the project. The Configuration Tools tab provides options for configuring hardware and wireless, including a shortcut to the GATT configurator. The Software Components tab is where you can save a lot of time during development by bringing ready-made code for pieces of functionality into your project with just a few clicks. Plus, when you bring in code for a hardware peripheral, the hardware pins are automatically configured for the hardware board you are using, and you can change them if you're running on a custom board using the GUIs. Initialization code is automatically added to the application startup code. Once you've added a software component, any header files can be added to the application code, and you can begin making use of the APIs to control the component's functionality. To find example code that makes use of these software components, search for an appropriate example in the Launcher's Example Projects and Demos tab. We're going to make use of quite a few software components in creating our Magic Wand application. First, we will add an EUSART software component to allow us to output debug messages to a serial terminal. Search for IOStream and then select the Services, IOStream, Driver, EUSART component. Then click the Install button to install the component. You'll be prompted to create an instance. This is where the hardware is associated with the component. Clicking Done to accept the default instance name vcom will set up the hardware for the virtual COM port. Opening the configuration for the component will reveal the hardware and pins associated with the component, and these can be edited in the GUI if necessary. The hardware pins are also reflected in the Pin tool, which can be accessed via the Configuration Tools tab or this shortcut button here. And here we can see the low-level assignment of the pins to the EUSART that have been created by adding this software component. If you don't want to make use of software components, this interface is where you can associate pins to hardware peripherals. To help with outputting debug messages, I'm going to add the log software component, which will make use of the IOStream EUSART we just added. We can find it by searching for log, and under Application Utility, we can select the log component and click the Install button to install it. Next, we'll add components for the red and green channels of the RGB LED. A search for simple LED will reveal the platform, driver, LED, simple LED component, which we can install using the Install button. This first instance, LED 0, is for the red channel, and I can click Done to accept it. I can click the Add New Instances button to add another instance of the simple LED component. In this case, LED 1 will act as the green channel for the RGB LED. Note that the simple LED component just deals with turning LEDs on and off. There are also other components if you want to drive the RGB LED using PWM. You can find that component in here as well by searching for RGB. But this is good enough for what we want to do in our application. I also want to add support for the two buttons on the dev kit board using the simple button component. So under Platform, Driver, Button, we can select the simple button component and use the Install button to install our first instance for button 0. And I can use Add New Instances to add the second instance for button 1. If you want to make use of these components with different inputs for custom hardware, and the same applies to the LEDs, you can go into the Configure dialog and change the pins that are associated with these components. But the offered instances are suitable for the development board that we've selected and that we're working with. The final peripheral to add support for is the accelerometer on the dev kit board. We'll start by entering ICM 20689 into the search box. This is the sensor fitted to the dev board. From the results, you need to install both the motion sensor. This is a low-level driver for the sensor. And also the IMU device driver. This is a higher level driver that integrates it with a common API that supports most of the accelerometers that we make use of on Silicon Labs boards. Then we need to install that higher level driver with the common APIs. Search for IMU, and then under Platform, Board Drivers, IMU-Inertial Measurement Unit, you can install this component to gain access to those drivers. The accelerometer is not automatically powered on with the board, so we need to make sure it is powered up at startup. If you enter a search for board control, you'll find this already installed board control under Platform Board. And if you click the Configure button here, we can find the control that will enable the inertial measurement unit when the board is powered on. We have now installed all the components for the hardware peripherals we want to use, but there's one final software component to install, which is the TensorFlow Lite micro component that provides access to the AI/ML inferencing. To install it, search for TensorFlow, and then you can install under Machine Learning, TensorFlow, the TensorFlow Lite micro component. You'll next need to click the Configure button for this component and enter 8192 into the Tensor Arena size box. This setting controls the amount of statically allocated memory available to the TensorFlow component. We'll be reusing a model from the Magic 1 Simplicity Studio demo, which requires 8,192 bytes. If you enter a value that is too small for your model, the compilation will fail, and you can use this to fine-tune your arena sizing. Adding the software components may seem like a laborious task, especially when done one after the other, as we did here. But they have saved us from having to write a lot of low-level driver code, higher-level APIs, and integrating their startup into our application. The use of these ready-made components really speeds up development time in Simplicity Studio. The code for the components can be found in the project files, and you can examine and even adapt the code to meet your requirements. Opening the header files, like this one for the simple button, will reveal the APIs you can call from your application code to make use of each component. There are a few machine learning example projects in Simplicity Studio that can be viewed by applying the machine learning filter to the example projects and demos. The Magic Wand example is where we are going to take the data model from to bring into our project. This example simply outputs the detected gestures to the serial port. For this dev lab, I wanted to show you how to integrate AI ML into a wireless application. This dev lab also covers creating Bluetooth client applications, as the majority of the Bluetooth example applications in Simplicity Studio act as Bluetooth servers. You can find additional AI ML examples in the Silicon Labs Machine Learning Applications repository on GitHub. You'll find a link to this in the video description. So how do you create or obtain an AI ML data model for your application? We actually have 3 different paths depending on the skills of the developer, which we split into 3 categories: Expert, Explorer, and Solutions. For Silicon Labs products, we define a machine learning expert as a developer that is very experienced with TensorFlow and Python. The expert tools require that a developer have these skills or is willing to learn them. On the other side of the spectrum, we have the machine learning solutions. This category assumes machine learning technology is used to add value to the product, but does not require any knowledge about machine learning, nor the need to learn it. Instead, these are black box solutions that can be used as a value-added feature to a product. In the middle, we have the Machine Learning Explorer. The skills expected here are to know the basic machine learning concepts and workflow, but to have an easy-to-use interface that curates the developer through the end-to-end workflow needed to implement machine learning as a value-added feature in their wireless product. By segmenting the tools into these simple categories, this allows a developer to understand what skills are expected of them in order to use the tool effectively. You can still have someone who qualifies as an expert use a solutions tool. This categorization just helps the developer to understand what skills they need to engage with a particular tool. Silicon Labs enables you through the following means of developing and deploying a solution. The software tools available for developing AI ML applications in EFR32 are 3 in general, which also correlate to the available development paths. At the expert level, we have the Silicon Labs Machine Learning Toolkit, a Python package that provides the means to process a data set and create, train, and validate machine learning models. This approach assumes that the data is gathered offline. At the Explorer level, we have partners like Edge Impulse, SenseML, and MicroAI, who provide frameworks to develop end-to-end solutions from data gathering to model creation, as well as ready-made applications to execute the generated models. At the solutions level, our partners can provide solutions libraries such as Sensory, or there are a number of system integrators who are experienced in this arena and can work with you to develop your AI ML applications. Once the model is ready, the TensorFlow Lite for microcontrollers framework is integrated into the embedded application to parse, interpret, and execute the model. We just looked at how tools are chosen based on application and user skills. This slide looks at the tools from a workflow perspective and how the different types of tools cover the workflow. One main takeaway is this line showing the ML Solutions tools bypass the whole machine learning workflow. ML Solutions tools just need the application-specific input, like typing in keywords, or using unsupervised learning to detect anomalies in the field. With a Solutions tool, you'll get a pre-trained, configured machine learning library that is ready for integrating into your wireless application. No machine learning expertise nor understanding of this workflow is required. On the other hand, the Explorer tools cover the complete end-to-end workflow, from creating the dataset to generating a library to integrate into your wireless application. There are 2 types of expert tool workflows. One is called Bring Your Own Data and works with the Silicon Labs MLTK. If you use the MLTK, it covers the training, testing, and conversion. You're expected to provide the complete dataset for model training and testing. The other is called Bring Your Own Model, which assumes you're using TensorFlow directly and will use the MLTK profiler to display the characteristics of your trained model, such as RAM usage, flash size, and CPU utilization. In this case, you are doing everything needed to create your production quality model and only using the MLTK to confirm this model fits. Ultimately, what you get is a range of options with a range of flexibility. but increased flexibility requires an increase in machine learning experience. The actual creation of data models is beyond the scope of this dev lab, where I'm showing you how to bring a pre-built data model into a wireless edge device. If you want to explore these paths to creating or obtaining a data model, you'll find links to further information in the video description. Rather than creating code line by line for this application, I'm going to use some pre-written code from GitHub. The code that performs the AI/ML processing is borrowed and adapted from the non-wireless magic wand example we looked at a moment ago. But I will walk you through the code shortly so you understand how it's constructed. You can find a link to the training examples GitHub repository in the video description. The source for this dev lab is in the DevLab Bluetooth AI/ML Magic Wand folder. From the web page, you can clone the repository using your favorite Git client or GitHub desktop. Alternatively, you can download a zip file with the files in it and unzip it into your local file system. To copy the source files into your project, locate the DevLab Bluetooth AI/ML Magic Wand folder you just cloned or downloaded. And in here, go into the source folder. Next, select all the source files in this folder, and you can drag and drop them onto the top level project in Simplicity Studio. When prompted, you need to select to copy the files, as a couple of these files are replacing files from the empty example project. And we just need to confirm that we're happy to overwrite these. Next, return to the Explorer window and go into the config folder. In here is a tflite folder that contains a .tflite file. This is the data model for the Magic Wand processing. If you go back up another level, you can take hold of the tflite folder and drop it onto the config folder in Simplicity Studio. Once again, we're going to copy these files. So this is the location where the compilation will find the data model automatically. Let's build the application by selecting the top level project folder and clicking the build button, which has a hammer icon on it in the toolbar. This compilation will take a while to complete, so while it runs, I'm going to step through the source code so you have an understanding of how it works. If you want to skip the build process, you can also find a pre-built binary file in the binary folder of the files downloaded from GitHub. The app.c file is the main application file that contains the high-level processing for the application. There are 3 standard functions in Bluetooth applications which you can build upon to create your application. The first of these functions is app_init, which is called once during startup, and you can put initialization code in here if your application requires it. These calls to the app log function are making use of the log software component we added earlier, and this is used to output debug messages to the UART. Next, we start a periodic timer. This is called regularly and is used to update the LEDs. And finally, the Magic Wand module is initialized, ready to start processing input from the accelerometer and feeding it into the AI/ML engine. The second of these functions is the app process action function. This function will be called repeatedly while the application runs. So it basically allows some time for the application to perform its processing while active. It's important not to put any blocking functions in here in order to give the Bluetooth stack time to run its operations as well. In this particular example, a call is made to the Magic Wand loop function where the Magic Wand processing takes place. And also there's a call to the button loop function in this module that reacts to button presses that are flagged by the button event handlers. The third typical function for Bluetooth applications is the Bluetooth on event function. This function is called by the Bluetooth stack to pass events up to the application for handling at the application layer. This function will be better explained by taking a look at a sequence diagram. In this application, this code is concerned with finding a device to connect to, making a connection to it, and validating that it is a device it can communicate with. When the Bluetooth stack is ready for the operation, indicated by the system boot event, the scanning for server advertisements is started. When an advertisement with a matching device name is received for our Blinky application, an open connection request is made and the scanning is stopped. A process scan response helper function is used to process received advertisements. Once the connection is open, indicated by the connection opened event, service discovery is initiated to the connected device. Each service will be reported with a GATT service event, and once all services have been reported, the GATT procedure completed event is raised. When the Blinky example service is found, characteristic discovery is initiated for the Blinky device. This works in exactly the same way as the service discovery. Each characteristic within the service will be reported with a GATT characteristic event, and when they've all been reported, the GATT procedure completed event will be raised. If the LED control characteristic is found here, then data can be exchanged between the two devices and the connection is kept open. If it fails to find a correct characteristic or service during this process, the connection will be closed. And also the connection may close if the device goes out of range or the device it's connected to is powered off. In all these cases, the connection closed event will be raised up to the application, and scanning for advertisements will be started once again and will re-enter the top of the loop and repeat this process to find a device we can communicate with. Information about these events can be found in the command and event section of the Bluetooth API reference, which you'll find a link to in the video description. Next, we have some application-specific functions, the first of which is the app tick timer callback function. This is called each time the periodic timer fires. The current state of the application is checked, and the two LEDs are updated to indicate the application state to the end user. These are using the APIs for the simple LED software component that we installed earlier. The button on change function is called whenever a button is pressed or released by the simple button software component. In here, flags are set to move the application onto the off or on states. These are acted upon by the button loop function, which is called from app process action. The app set state function is used to request a state change. It is called by the Bluetooth processing to indicate the connection status. It is also called by the button and magic wand code to transmit Bluetooth commands. When the state is changed to on or off, a Bluetooth write command is transmitted to the light. But only when the device is connected is it allowed to make those changes of state. The final function in app.c is button loop, called repeatedly from app process action. In here, the state change flag set in the button event handler is checked, and a call is made to app set state to act upon it. There are three modules that work together to provide the magic wand processing. Accelerometer.cc handles the processing for the accelerometer. Predictor.cc handles the AI ML processing, and magicwand.cc glues them together and provides the interface for app.c to use. Let's take a look at how these modules interact during initialization, which takes place from the magic wand init function called during startup from app init. The model and interpreter are retrieved from the TensorFlow component. The accelerometer is initialized, including configuring an interrupt whenever a single reading is ready. The accelerometer module collects multiple readings into a buffer. A loop is run until the accelerometer has filled its buffer, ensuring there is data to feed into the AI/ML model once the code leaves initialization. The main processing for the magic wand takes place from the magic wand loop function, which is called each time app process function is called. The multiple readings from the accelerometer are placed into the model input buffer with a call to the accelerometer read function. The interpreter's invoke function is called to process the input data against the model. The output from the interpreter provides probabilities for each gesture that can be recognized by the system. This output is then fed into the predictor module, which averages across multiple results and ensures confidence in the best results in that they meet a required threshold. If the threshold is not met, no gesture is returned. Finally, the gesture is fed into the handle output function. For the O and L gestures, which are used to turn the light off and on, the app set state function is called to handle that process in the main app module. Now the application is compiled, we can find the .s37 file in the binaries folder, right-click it and select Flash to Device. In the Flash programmer, I'm simply going to click Program to transfer the binary, and this will place it alongside the bootloader we programmed towards the beginning of this workshop. There's no need to erase the Flash at this point. For the moment, I'm going to keep my Blinky application powered off so we can observe the connection process. On the one device, the yellow flashing indicates that it is scanning for a Blinky device to connect to, or is in the process of checking that the correct service and characteristic is in place in a connected device. I'm watching the debug output from the wand in a terminal application, running at 115200 baud, 8 data bits, no parity, 1 stop bit, and no flow control. Next, I'll power on the Blinky device. When the wand connects, it will turn the LED into a solid yellow colour, as the current state of the Blinky is unknown. You can see the output in the debug showing the process that the device went through during connection, discovering the services, characteristics, and finally going into the connected state where the light can be operated. To operate Blinky from the buttons, I can press button 1 to turn the light on, and the LED will turn green. We can also see the debug output for the button changes, the application state changes, and the Bluetooth transmission. And button 0 will turn the light off and set the LED to red. For gesture control, you need to hold the board flat in front of you with the USB port towards you and draw gestures in the air as if drawing on a chalkboard. To control the light with gestures, you need to draw uppercase letters in the air in front of you, an L to turn the light on, and an O to turn it off again. So that brings us to the end of this dev lab. We've taken a pre-built AI/ML model and integrated it into a Bluetooth client application that we can use to control the light with gestures in the air. You'll find lots of links to further information in the description for this video, including Bluetooth development, AI/ML development, and also the various pathways that you can follow with our partners to help you create your data models. There's also a Bluetooth voice-controlled AI/ML Pac-Man demo that you can run in your browser. Thanks for watching.